Professor,
Yes.
you were muted for a while there.
Oh, okay. I think I was waiting. Oh, it's already time. I thought it was still early. Okay, good morning. Now we should start. I was posting a question for attendance. It's one of those maximization questions. Let's finish this question. I'm going to talk about the plan for tomorrow. Here we have the question. It's a question about calculating the number of unit to maximum profit. So for this kind of question, after you read the question, you read the comparative term. It says we want to yield the maximum profit. So we realize that a quantity that needs to be maximized is profit. So if you want to find maximum profit, you have to find a way to calculate profit. The idea of the profit is that you are making an income or a revenue, but then this is done by making and selling products. So the selling part earns you money, but the making part normally costs money, such as equipment costs, material costs. So there's a lot of costs involved. So in this case, we were given the formula for the revenue. We were also given the formula for the cost. So if you want to find the profit, you have to take the revenue function minus the cost function. And that's basically the idea for how to set up a target function. And that's what I was writing over here. So if we have a way to calculate revenue, we have a way to calculate cost, then the calculation for the profit will be, let's take these two functions, subtract them. So here you have the f of x. I was using f of x to represent the profit. So identify that whenever you write a quantity f of x, you mean the profit equal to the two functions subtract. Then we're creating a formula for how do we calculate the profit. And we're trying to find the maximum value for the profit according to calculus. In order to find the maximum minimum, you essentially need to study increasing and decreasing. But normally for a function that is changing, that is sometimes increasing, sometimes decreasing like this. All right. So whenever it's increasing, it would have zero derivative. If it's decreasing, it has if it's increasing, it has positive derivative, and decreasing negative derivative, and increasing positive derivative. Whenever you see a maximum or minimum, normally that's where when the derivative either equal to zero or undefined. So these are the reasoning behind why do we want to find the derivative. So normally if you find the derivative functions that equal to zero, that often indicated either a possible maximum or possible minimum. These are the key idea that we had in 3.1 and 4.3 when we are talking about maximum minimum. All right, let me remove that and we're gonna actually calculate the derivative. And then we will set the derivative equal to zero because those are the key points between increasing and decreasing. If it's increasing, the derivative will be positive. If it's decreasing, the derivative will be negative. But in between the increasing, decreasing, the derivative will be either would equal to zero. So the zero is useful. So when you find the point when it equal to zero, you can then determine the point, the interval when it's positive or negative derivative. So we're going to calculate the derivative. If this is going to be 2 times 0.5 x 1, we have x the power minus 1. So this derivative is really x. And then we minus the negative 10 has the derivative, negative 10x has the derivative negative 10. And that's all we have. So if we're trying to find derivative one by one, the last number negative, so you have zero derivative. We're trying to find the equivalence, we're setting this equal to zero. Then it becomes equation solving, right? So we started out talking about derivative, but when you already determine what you to solve, and that's what we're focusing on. So that's becoming an equation. Solving this equation, we would have, you have the answer, right? X equal to the x value represent the number of unit, and then the function f of x representing the actual cost. You want to maximize the profit. You want to maximize the profit by changing the value for the x. You see how we solve for the x? It's actually after you're solving for the x value from there, like what's the x value that give you the quantity. The function have a negative square term, so all the other one are degree 1 term. That's the only square term, which is negative, so it's actually a parabola opening down. So we can see there is a maximum. It will be increasing, then decreasing. So there's a maximum right at that point that you would solve. And then I'll let you finish solving this equation, combine the number and solve the x value. That should be the number unit that we need to maximize the profit. Let's finish this question for attendance, and then let me know how's your preparation for the test tomorrow. Okay. Okay. Try to get small. I have the scanner on, so if you're online, you can choose your answer on the clicker page. It's a degree 2 equation, so it's either open up or open down with the completely. So this one, because it's a negative x, negative 0.5 squared, so it's open down. So it's increasing, then increasing right there, that's the maximum. And that point has to be when the derivative equal to 0. So find the point when the derivative equal to 0, that's when we achieve the maximum value. Let's see if you guys, yes?
Could I have my Flickr link again? The chat I usually scroll down to get it has disappeared, I guess.
Okay, Jesse?
Yes, ma'am.
That's the link. Let's go to the page and make sure everyone has answered. You guys still calculating? I'm still waiting for 2 more answers. Those are the calculation. If we solve this equation, you can see the 30 minus 10 is a number, and the x is just minus x. So if you take the 30 minus 10, you get 20. So it's actually 20 minus x equals 0. So you add the x to both sides of the equation, and you have 20 equal to x. That's pretty much the solution. X equal to 20 is where the function reach the maximum. You can also, if you want to, you can graph the entire function. And then you see that it's actually a degree 2 equation because the 30x can be combined with negative 10x. If you write it into the ABC form, it's negative 0.5 x squared plus 20x and then minus 3. That's what it is. So the degree 2 term is a higher degree, which indicated the overall behavior like this. And then right here in the 20, it's when it reached the maximum function value. That's maximum. The function, this is the profit if we want to calculate it. But the question wanted to find out the number unit, which is why we answer the x value. I hope that you finished your calculation. Okay. Let me try to solve. Yes, so the answer should be 20 as in the calculation, and that will be today's attendance question. All right, let's talk about the test tomorrow. Have you guys take a look at the practice question? What I was looking at how much work you've done on your homework for chapter 4. I have to say by now there are quite a few of you that haven't finished all the homework yet. So I'm a little bit concerned about how ready are we for the test. But another thing is we really don't have a lot of time left. Other than today, tomorrow, we have next week, Monday, Tuesday, and Wednesday. Wednesday will be the last day of class. So even if we want to push it later, we only have maybe Monday. Right, so these questions, they're actually, I attach a video that contains the solution, just in case you are not sure how to solve it. So, my phone every morning does that. So the first question is from section 4.2, and then question 2 is for differential. These are the two that we had some, relatively 4.4 and 4.2 are the, compared to the other 3 sections, are slightly easier one. And that's the optimization question. This is also an optimization question with the volume involved. We had that homework. And then this one was on the cost of compute. That's an optimization question. This is a related rate question. So I had the solution already posted also in the question set. I did mention some of the YouTube video that will give us the process of that solution. Any of those questions you want to start talking about it, right? Like question 7 is the homework that we had, right? The renting the car for the cost, and then how to produce maximum income. So 7 is one of the homework question we had in 4.3. So some of the question looks familiar and some of the question are not so familiar. The continual question was also one of the question that we had in our homework. So definitely if you are able to finish your homework, you will be a lot more prepared. I only see a few people that did all the homework. Must like quite a few students are still very behind. Wonder, do you have any comment, any suggestions?
I know it's not schedule wise ideal, like you said, but
Mhm.
and I know I probably already should be prepared for this test, but Monday would work better for me because if it's possible, because there's an organic chemistry exam Thursday or tomorrow as well.
Okay. Okay. Yeah, so I let me try to collect the whole class opinion as I'm gonna put that kind of question over here. So let's say but that's my question. It's gonna be a survey. I think that yes, that's some note. So I want to find out how many of you prefer pushing the date later. If we're not changing it, then today's Wednesday, tomorrow will be the test day. If you feel like having a few more days will be helpful for you, then we'll vote on it. So add it to that. Trying to add to our class. Let's go back to. Yeah. Okay, so you guys can choose your answer. Let me turn on the scanner. So I want to find out how many of you prefer changing the date. It's either A or B. So let's vote on this. So let me see what's now. Okay, so I do see a lot of yes. I remember yesterday you want to get it over with. But I kind of understand this is you. So since most of us did answer yes, so I guess we're changing it to Monday. So that will be the decision for today. Okay. So if we're changing it to Monday in the meantime, I should send out announcement so everyone. Well, I guess everyone is in class today, so assume that counts as an announcement that we're moving the test day to Monday. Normally I would send out a Georgia review announcement so everyone will know. That just for students that's not attending. So if everyone is here, we all know that it's happening. So next Monday will be test 4. That will leave us some time now, right? So today and tomorrow we can continue preparing for more homework. But I do feel like we were doing the homework question already in class. I was hoping that you guys would open your web homework and doing it with me. I wonder, did I do it too fast? That caused you not being able to follow, or because I see many of us, I did more homework than some students. I did it on my account. I did like half those sections, and then for many students, they were. So I was like a little bit at a loss. If I can't get you to follow the example during class, it will be harder for you to do it after class. It's just going to be more time consuming if you do it by yourself.
I think sometimes you go fast, but I'll ask you to slow down. But if nobody online is saying anything, and you don't know to slow down, you know.
That's probably like on my fault too, because sometimes like I'll message in the chat, but obviously you're working on something, so you don't see it, and I should speak out on my microphone. But a lot of the time, I think the only time it gets too fast is just when you start doing the calculations with the calculator online.
I see.
Sometimes when you start going back and forth really quickly, that's when it starts to get lost.
I understand. I mean, I'm only showing what's on the computer. Sometimes I did the copy and pasting way too fast. Yeah, I really appreciate it. I think using the microphone is easier as far as communication goes. Maybe I should change the window more often to the main window in Teams. Oh, I see. Well, we are having all the classes recorded, so if you want to watch the recording later, almost all of our classes has a recording online. So you can actually follow those whiteboard example after class while pausing it on every page. So it's possible to go back to those examples. Yeah, I think everybody have a different pace. I would hope like some of us could benefit if we were doing the homework during the class together. Okay. About the test 3 practice question, do you have any one of those questions you wanna do it together? Like I can explain now. Any of those solution that was posted, if they look messy or confusing, I can explain them during our class session. Those are screenshot of what I did before, like for previous class. So that was solution for the question 1 is L'Hopital. So whenever I write LH, that's when I apply L'Hopital. Like for part A, we apply L'Hopital twice because if you apply one time and the numerator denominator still achieved arriving 0, and that means you can't calculate it by 0 divided by 0. If it's 0 divided by 0, we cannot calculate it. We apply L'Hopital one more time. Now it's no longer 0 divided by 0. That's why we can finish the calculation. The second question, you only have to apply L'Hopital one time. You do have to remember the formula for derivative 7 to the power x is 7 to the power x times ln of 7. Derivative 6x, the derivative is 6x times ln of 6. So basically derivative a to the power x equal to a to the power x ln of a. I write the formula on the side. So whenever the question needs a formula, I write on, like I block it out to the side. So you can see in that rectangular box, there are a couple of formula for derivative calculation that was mentioned during these questions. This solution was okay, so it's not as messy as some of my solution is. That solution for question 1 using L'Hopital. The second question is the section 4.4 homework about differential. So if you haven't finished your 4.4 homework, maybe you should try to compare what we have here with what you have in your homework assignment. So both of these questions have a root function. So if you want to, well, this is actually the same question with different numbers. This is one of the homework questions. Because we have a root, we need to know what's the derivative of the root of x. And here we have on the side is the formula. So when you apply a formula, you know the derivative of 5 root of x is going to be 5 times 1 over 2 root of x. So the calculation will be, when you calculate dy, you're going to need derivative. But when you calculate delta y, that's the change. So you calculate the first y value minus second y value. So that will be an example that you can follow when you are doing your 4.4 homework. Any question? So I suppose this one, at least the organization of the solution on the page is not, it's not too confusing. That's 4.4 homework. And then there's question 3. This is also from 4.4. Essentially, we plan for having 2 questions per section. 4.4, one hyper question is calculating differential, which is kind of like the last question. So number 3 is approximation. So you want to find a way to find the approximate value of a calculation. For example, square root of 102. We know square root of 100. So square root of 102 should be something similar. Since f of 100 equal to 10, f of 102 is something close to 10 plus something. To find out that something, the change, you calculate dy. So what's dy? dy is derivative times dx. The derivative have to follow the original function. You have to find your f of x to find f prime of x. And then once you have the derivative, you plug in the number that you begin with. In this case, we plug in the 100 for the derivative, and we plug in the dx is calculated by the subtraction. So dx is actually 2. In this example, so we figure out the change is 0.1. So the final answer will be 10.1 in the first approximation. Any question? These are 2 examples that you can follow when you are doing your 4.4 homework for approximation. That's probably something I will try when I pick out question for the actual test. So since it's almost the end of semester, I'm probably going to stay really, really close to the practice question set. So there's no surprises. Any question?
I know we talked about it yesterday, but I would probably prefer if you could sit closer to like the word problems, so like the 4.3 and 4.1, if you could stick to the examples you put on the test.
Okay.
Because I went back and I watched those videos that you had linked with it, and that makes a lot more sense than some of the homework questions, in my opinion.
I see, I see. That's the reason I posted those videos. I
Yeah.
feel like those YouTube videos, they explain the question really clearly.
Mhm.
And then it also kind of give you a different perspective than the way I was doing in class. So the word problem, yeah, I think, since we are so close to the end of the semester, I won't put anything surprising on here. Of course, I will change the number, but definitely not changing the questions.
In like the corner.
Uh-huh,
Okay.
yeah.
I did have two questions on 4.5.
Okay.
It's the two graphing questions at the end. I'm just a little confused.
Okay. Yeah, so feel free to like read through the rest of the solution and like I said, the question itself already have a video explanation on how to solve them. So if any of those solution are not making sense, there is the file itself. As far as the word problem, I posted attached a video link to it. You can watch that video to explain anything similar to this. How do you solve it? And this is a video explaining this question, and then there's a video explaining this question. So these word problem, I'll have a link that explain the solution. The Newton's method is a systematic way to solve an equation that there's no shortcut. You have to work through the Newton's formula. Right, since Ray asked for the 4.5, that's also the Newton's method questions. Maybe we can try again. And then yesterday, a few of you are asking questions in the chat. I didn't notice it at first, so maybe now we can also practice together. I reopened all of our homework. I pushed the date until May. So you have plenty of time to go back, work out any of the past homework that you didn't do to increase your homework grade and also to make sure that you get sufficient practice. That way, I'm hoping that you finish all your chapter 4 homework before Monday. That way you will be prepared for the test. See, this is what I did for 4.5. I already did 4 of them. And then there are a few of you that had not tried the 4.5 yet. The graphing question you were talking about,
Problem 7 and 8.
7 and 8. Okay, number 7 is, you see, there are two functions. One is y equal to 3x. Maybe I'll try to draw on this since I'm explaining it online in the video. I guess it's easier if we can write. That way it's easy to tell what I was talking about. So this question is asking us to find a solution between two functions. Whenever you want to find a solution or intersection between two graphs, you have two functions. And this first function is a line. And that's the one you see in the graph on the right, the line. All right, and the second one is y equal to tangent of x. That's a curve. It's this one. The actual scenario is, well, there's many tangent curve. Tangent goes this, this, and this. Then right here, you got a line there. Now we're looking for intersection between the line and the tangent curve. That's what's happening. So you can see the approach that we had is there are two solutions. The y equal to 3x and tangent has two solutions. One is right here, and then you don't have to guess. That one is x equal to 0. Because you see, if x equal to 0, 3 times 0 is 0, and also tangent 0 equal to 0. So this are passing the point where the x equal to 0, the y equal to 0. That's the point, 0, 0. Okay. They share the same point. They share the point. The common point between the two graphs is 0, 0. Now we're solving for the other one, which is right here. Okay. Are you having identical question or slightly different one?
Slightly different.
I have 3x. You may have 4x or 2x.
And 4x.
Okay. So we are trying to figure out the other answer from the graph. This is the benefit of having the graph there, because you see the solution we're looking for. We're only looking for the x values. You go down, where's the x value? There. Okay. And you might guess what's that answer. That's 0.5. This must be 1. and this is 1.5. So right between 1 and 1.5, let's guess 1.3. Okay, we're not saying the 1.3 is a solution. We're saying 1.3 is close to the solution if you have the graph. Are we okay there? So that's gonna be what we're solving. We're gonna start with x0 equal to 1.3. 1.3 is gonna be our first answer. What are we trying to do when you are pairing two equations together? You have y equal to 3x. You also have y equal to tangent 3x. To find the intersection, you pair them together. The y equal to this y, this x equal to that x. Because they're equal, you can pair them together. Essentially, we're solving that 3x equal to tangent of x. That's what we're solving here. So if we're applying Newton's method, we have to have the f of x. So then we're putting them together, realize that solving the intersection involves solving 3x equal to tangent x. So we're solving for that. And then you can try plug in 1.3 to 3x and you plug in 1.3 to the tangent. They shouldn't be too much different. It should be pretty similar. So now try to get rid of everything else. And now we're solving this equation. This equation is 3x equal to tangent of x. If we're applying Newton, we have to make sure they're on the same side equation. So subtract tangent x from both sides of the equation. You have 3x minus tangent of x equal to 0. So basically, this equation we want to solve is the same as this equation. Not same equation. So we did a slight change because if you want to apply Newton to solve it, then the right side equation has to be 0. So we don't want to keep the tangent on the right. We have to move the tangent over, but the tangent has to be subtracted. Are we okay? So that's our f of x. We also have to find the derivative. So we would go f prime of x is equal to the derivative 3x is 3 and derivative tangent of x is secant square of x. So that's our derivative. Let me try to guess how far we are. I'm guessing 1.3. I'm gonna do multiple time for the Newton. So that was not close enough. So we're gonna try Newton to get it better. So the Newton's method will be your second calculator after the initial guess, initial number 1.3, which is, you see the graph, it's already pretty close. So to get from there, we go x1, which equal to x0. We change from x0, change up from it. It's going to be the function value at x0 divided by the derivative value at x0. So doing repeated calculation of the same thing. You need the 3 number. You can see you need x0, which is 1.3, minus the function value at 1.3 divided by the derivative value at 1.3. Now, both of these functions needs to be calculated. So I guess before you are able to put it in, if you calculate it. So what is f of 1.3? Up there we have the function. This up. F of 1.3 is 3 times x minus tangent of 1.3. Okay, so that will be the calculation for the function value. I want to be able to have the number for the numerator and denominator. That way the calculation will not be ambiguous. Make sure that we are as clear as possible with our steps. So I get that number. Try to stay. Are we okay? You probably need your own calculator. Of course, during the test, you cannot use Google. But you're going to do something as what I did, which is pick up your calculator, goes 3 times 1.3 minus tangent of 1.3. Make sure your calculator is in radian mode. If it's degree mode, it wouldn't be right. Most of the common calculator, like what's in Google, and lets you identify that's degree. Most of the time, the computer automatically assumes that you were doing radian measure. Okay, you're getting the same number. If you're getting a different number, your calculator probably is setting a degree measure. We want radian measure, radian mode. Are you getting the same thing? If you're using your calculator for Newton, so for the Newton's method, so for 4.5, you'll make sure that you are able to use your calculator. I'm guessing that yesterday you were doing fast. We okay?
Yeah, I just get different numbers.
Okay, so you're double checking your number?
Yeah.
So this is what we need for the function value, realize it, base. Copy that number over, but if the space is small. Okay, so this is the function value, and we also need the derivative value. F prime of 1.3 is the derivative, and the calculation is 3 minus secant square of 1.3. Then if your calculator do not have the secant function, you would go 1 over cosine square of 1.3. Or if your calculator does not accept cosine square, you can also do 1 over cosine of 1.3 and then square. So it will be the same. So I'm gonna 3 minus secant square of 1.3. I'm gonna use a calculator. You should pull out your calculator and see if you can follow me and get the same answer. So that's the 3 minus secant square of 1.3. And I copy that over. Right now we're ready to calculate the x1. So then x1 is equal to 1.3 minus the numerator. Forget the number, but the denominator I already have it. And numerator is supposed to be the type it 0.297,897,55203. To make sure the calculation is accurate, I put in as much decimal as I can. So here are the calculations. I give you this. So you can see it's still 1.3, but it's way more accurate than 1.3. And that's the whole point. You gotta have a starting point that is nice and close. Then you don't have to do a lot of Newton's process. So this is a one application. And then now we have our x1. X1 is a little bit better than x3. 1.3 is close, but it's different. So now I'm putting that one in. So I don't have to try second time. So that will be trying the Newton's method one time. And then let's try it one more time. So that's x1. x2 is equal to x1 minus the function at x1 divided by the derivative at x1. So we're going to try the Newton one more time. Okay, so x1 is the number that we just copied over minus the function value divided by the derivative value. All right, I used to calculate it, but realize going back and forth to the calculation also takes time. Let me just go ahead and put in the function value. The function value is, well, it's going to be long if I try to put it in there. So the function value is f of this number, and then it equal to 3 times x. Go back up. 3x minus tangent x. So it's 3 times the input value minus tangent of the number that we just copied. Okay, so that's the calculation for the numerature. Because I keep so many decimal, I realize that it's not easy to put it all in. So that was the calculation. So you can see it's pretty close to 0. I guess it's not arriving at the close answer. So we go, this is equal to this number, and then let's try to fit them in one line. And that is goes into the numerator. Put in here. Okay, so that's the numerature. The denominator is supposed to be the derivative. Now we have to calculate the derivative. Derivative at 1.3271429 1.3362. Okay, so we need to calculate derivative. So how do we calculate it? It's 3 minus secant square of the number. That's the derivative formula. You can go back up and see f prime of x equal to 3 minus secant square of x. We putting this x value into the secant square. That will be the calculation. Again, if your calculator do not have secant square, you can use the 1 over cosine square as our secant square. That's the calculation. And then we're gonna put this into the denominator. So that would be the calculation. Two negative make it positive, but then the negative in the numerator and the denominator, they'll cancel. That will be the calculation for x2. It's a lot to copy. I would doing the same paint after I paste it in there, it won't copy. So let me try to writing the calculation. All right, so essentially it's the number that we get earlier, the derivative. So then the numerator and denominator both being negative, cancel. So it's 1.32. Let me try to go up. I'm gonna do copy the x1, like the calculation of x2. X2 is equal to x1, which is 1.327142993362 minus the function value 0.04122. The negative was canceled. 0.86929. So that this is all we need. The x1 minus the function value divided by the derivative value. That's the x2 calculation. Let's see how far we get from there. It should be even getting closer to 1.3 something. So let's put this in there. Suppose we don't have to try too many times on Newton. So we're finally arriving at the answer that the computer are happy with. So we tried it Newton 2 times. Is that okay?
I'm so not.
Okay,
But I know what I need to do.
right, you might have to do a few rounds of this Newton to get close enough. That's the question, that's question problem 7, and if you wanna look at question 8. Okay, so this is finding solution for e of x equal to 5x. As you can see in the picture, there are again 2 solutions. This time the computer wanted us to find the left solution and the right solution. Like you said, which one are you solving for? You have to estimate it close enough that your initial solution is not too far. So what you can do is you can see that was 1, this was 0, and now it's, let's see, 0, -1, 0, 1, 2. That must be 3. So this answer on the right is 2.6. The one on the left is 0.3 or 0.2 something. So we can start somewhere close enough and do the calculation. All right, so let me go through the same similar process. I kept a lot of decimal, and that's why the writing is longer, but I hope that it kind of explains the main idea of the Newton's method, which is like this. And that's the formula for calculating x1. This is the formula for calculating x2. The longer process is because I copy the long decimal to maintain the accuracy. If you only want to keep 5 decimal or 6 decimal, that should be sufficient. When I was doing, I copied like a 9 decimal. That's what's making it long. And let's see. So let's talk about question 8. The equation we're solving is this one. This is the equation. So we're essentially solving that e to the x equal to 5x. And again, if you are using Newton's method, the right side has equal to 0. So we subtract 5x, and you have e to the x minus 5x equal to 0. and that's going to be our function value, the function that we follow. Again, with the function identified, you want to find the derivative of your function because you're going to need a derivative e to the x is e to the x, derivative negative 5x is negative 5, so that's a derivative. And let's say we find this solution on the left. We were trying to find a solution on the left. It's roughly 0.3. So I'm going to start with x0 equal to 0.3. Okay, so we want to see how many times do we have to try it. You can start with x1 that equal to x0 minus the function value at x0 divided by the derivative value at x0. So that would be the formula, the Newton's formula. This is a Newton's formula. And then we start with this 0.3 minus the function value at 0.3. It shouldn't be too far from 0 since we are choosing a number close to the solution already. And divided by the derivative at 0.3. Okay, so this calculation is this. We do 0.3 minus the numerator is e to the 0.3 minus 5 times 0.3. So I'm not doing the long decimal, I'm just putting the calculation here. The denominator is going to be e to the 0.3 minus 1. So that will be the actual calculation. And then we can choose to use the whiteboard as our calculator instead of going on to Google. So we can do 0.3 minus, and the numerator, you make this larger. The numerator is e to the 0.3 minus, what's it, 5x minus 5 times 0.3 divided by e to the 0.3 minus 5. So that will be the calculation for the updated answer. It looks like it's not close enough, but then we can try again. This number is going to be your new number. This is going to be your x1. So that replaces 0.3. Did I not be able to copy? Which one copy it? Let me copy. So instead of 0.3, we're going to start with this new number. And then that also replaces where you have that 0.3. Okay, and then replace the 0.3 in the denominator as well. Okay, so that will be the Newton's method calculation on the second try. Did I find the wrong? Okay, so that's still not the final answer, but we're getting close. I start with 0.3, now it's 0.29, 259, and let's see, so we replace this with a new number. It's iterative because all the previous answers are being applied to the subsequent calculation. This number is replaced. Replacing this. This way I don't have to go back and forth between the calculator since I'm doing it with work anyway. So this is replaced with a new number. Let's see. That's already 50%. I guess I should see that before. This is already accurate enough, and the computer is saying that we got half of our question answered. So that's, you can see we got this one, and you can see that they're not that far behind, far different. Like 0.259171. The earlier one was 0.259171. They're pretty much the same as far as the first three, 6 decimal. So it's already 6 decimal accuracy between these two numbers. And that's why the computer thinks it's okay. It's already the number close enough. For the right side of the solution, if you look at the picture, what are we getting close to? It's somewhere here. that's 1, that's 2, right? So that's is 2.5. So we can start with 2.5 and do a Newton's calculation. So what the Newton's method saying, identify a close enough answer, subtract the function value divided by the derivative value. The function value is e to the x minus 5x. So you go e to the 2.5 minus 5 times 2.5. So that's e to the x minus 5x. Denominator is e to the x minus 5. So it's e to the 2.5 minus 5. So that will allow us to calculate one number. Let's see. That's already close enough. So for the second one, because I chose the answer, the initial answer is so close, with one attempt of Newton, we already find close enough answer. You can see over here, we started out with 2.5, but then the new answer is not too far from 2.5. It's like 2.54204.542. You can also graph the function e to the x equal to 5x into decimals to see the answer. And you can see from the picture that the intersection is that number, the x. I hope that helps.
Can you go back to the calculation?
Mhm.
Where did you find the 0.3 to start?
The 0.3, I watched the distance. You see, that's 0, that's 1, that's 2, that's 3. So this intersection, if I go down vertically to the horizontal axis, it looks like somewhere between 0 and 1, but not in the middle. 0, it's not the direct middle. It's a little bit to the smaller side from 0.5. So that's, I'm guessing, is 0.3. You can also try 0.2 or 0.4, but that might mean that you have to try a couple more times. I think if you choose the answer really, really close, you don't have to do a lot of round of Newtons.
Okay.
Yeah. Any other question? I hope that can explain the Newton's method. So the Newton's solution, you can try with a graph or try the earlier one. The first few questions is when you already are given the initial number. So you start with -1, you try it one time, try it second time. And these are the function value, and that's the derivative value in the denominator. Basically is you pick one answer and then you start saying from this answer, how do we get closer to the number? Newton's method made it possible for you to have a new number that is closer to the true solution. If you are not too far, sometimes when we are too far from the answer, then the Newton's method, the fundamental reasoning is using tangent line to approximate the curve. So if you pick a point that's too far, the tangent line went all the way far away from the true solution. That's why sometimes it takes like 7 or 8 try to have the number finally converging. There's a mathematical term called converging, means that the limit it looks like the limit exists or the limit is near. That's the idea of converging. So if there's a limit, then things are converging. If there's no limit, then it's not converging. So the idea of converging is kind of interesting. Question? Did you finish all your 4.5?
I just have problem 8, but problem 7, it took me to 6.
A 6
Yeah.
attempt. But sometimes we see hope. Sometimes I try it, I see the number not getting closer. I don't feel like it's hopeful. So I want to try something closer. Fundamentally, Newton's method would eventually lead you to the right answer. But then you don't want to keep trying it because every attempt takes a minute to try the derivative, the function, the derivative, the function. So you want to try something closer. So maybe you want to try 1 or 2 times of Newton, then you have your solution. So the initial number is really useful to make it close. Any other question from the test or from the homework?
Could you go over question 2 on that same section real quick?
5. Okay. Let me see. Number 5. I felt like we've done this yesterday. This is also one of the test questions on the test file, we had the approximation problem is calculating a cube root. You can find it here. I think it's question 2. Oh, it's number 3. Cube root 124 is what we're trying to find out on the test question. That's question 3. You can look at the solution for that one. But in the meantime, let's start with our way. That was approximation. This is using Newton. I guess they were trying. They're not exactly the same, but it's along the same line. Okay, so we're trying to use Newton's method to approximate the value for cube root of 40. And since we're doing Newton, with Newton's method, you need an equation. So the number by itself, there's no equation. So we would create an equation by saying, let's make x equal to this number. Cube root of 40 equal to x. Okay, now we have an equation, but this equation will be hard to calculate is derivative. So we're gonna, since it's the equation, we can apply any skill or technique that we can apply for any equation. So we're gonna cube both sides of the equation. If you cube the left side, it's gonna be x cubed. If you cube the right side, this is what happens, cube of the left and then cube of the right. The cube is a degree 3 power. It will cancel the degree 3 root, which give you 40. Okay, fundamentally, the cube function is an inverse of the power function. So if x to the power 3 equal to 40, then x is a cube root of 40. So that's really the fundamental idea. When we first started defining root function, it is for conquering the inverse of power function. So anyway, now we have this function that we actually are solving. We're solving for the solution x cubed equal to 40. So the function that we work with will be f of x is equal to x to the power 3 minus 40. So that's going to be the function, and then you can see when you want to apply Newton, you have to make sure that right side is 0. So now if it's not 0, you subtract it. So you subtract from both sides of the equation, you get x cubed minus 40 equal to 0. Once the other side of the equation is 0, then the left side of the equation will be your function. So this is how we try to figure out the right function to work with, especially for this kind of question. It's in the question itself, there's no function, there's no equation. So we creating an equation, now creating our function to work with using the Newton's method. Because Newton's method essentially is a function. It's applying the tangent line of the function. If we don't have a function, then there's no Newton's method. The derivative of this function would equal 3x squared. And then the 40 obviously does not have, 40 has 0 derivatives, so we don't have to do anything for the 40. Now we have it. We have the function. We also have the derivative, and then it says in the question that we're going to start with x1 equals 3. From x1 equals 3, we can start calculating x2, and the solution is already there, but you can see how we calculate it. x2 is equal to, it's going to be an updated number from x1, so it's x1 minus, start with x1, start doing small changes to x1 to get to your x2. So equal to function value at x1 divided by the derivative value at x1. That's our Newton's method formula. And then in this calculation, you're going to need 3 number. You need your x1, which we already have. That's the 3. You also need a number for the function and a number for the derivative. Okay, this maybe we can do it faster by containing in there. The x1 is 3. And then what's the function value? And so 3 minus a fraction. Okay, now the numerator is supposed to be the function value. You plug in 3 into your function f of x. That's x cubed minus 40. That's the function. So we have 3 cubed minus 40. That's a function value. Make sure you have parentheses for it because we want to make sure the calculation order is right. Denominator. In the other pair of parentheses, we need to find the derivative. Going over to the right side, f prime equals 3x squared. So we were supposed to plug in the number 3 into the derivative. So it's going to be 3 times 3 squared. And that will be the calculation. And then now that's all you need. And then the 3 times 3x squared, that's a 27. Then the 3 cubed minus 40 is actually 13. So essentially 3 plus 13 over 27. That was the answer. You can also simply put in the numerical value, the decimal value for it. If you put all these into your calculator, like this, that calculation is going to give you this. And that was the answer we were supposed to put into what the last time I tried to put in this number. That was first attempt. Right, the second one you try this again, but then you were calculating x3. So now that we had the x2, now with x2 as the beginning point, we're going to calculate x3. x3 is x2 minus by the function value at x2 divided by the derivative value of x2. So that's how you calculate x3. It's iterative because the previous number is being applied to calculate the subsequent number. So you have this number, that's the x2, and you have to minus this number, function value divided by the derivative of this number. So what's the function value? It's x cubed minus 40. So this number that we had as x2, you have to find its cube power and then minus 40. That's the function value. In the denominator, we need the derivative. It's 3 times the x value, which is this, and then divided by 2. So that's the derivative calculation. And it's way longer than I can fit in one line. And that will be the calculation we need to put in the calculator. And I have it already done. That should be the number. You can also double check that with any other calculator. So that's the number we get after all is calculated. And so you can see we go from 3, and then we have 3.481481, and then we have 3.4210329. So the answer is getting closer and closer to the true answer of the cube root. We're solving for the cube root. And going back here, all you have to do is enter. So that's number 2. Once we find out the function formula and find out the derivative, the rest is similar to what we did with all the other Newton's practice. I hope that answered your question. Do you have a different number?
No, I got part A right to it. I just couldn't, I guess the way I was entering in part B.
I see. Any other questions? About the test or any more questions? Okay, if we have tests on Monday, then let me go through a little bit of something in chapter 5 because we're a little bit short on time. I was planning on to cover a lot of it, chapter 5. It's going to be the first chapter. It depends. In Calc 2, some of the instructors start with chapter 6. They assume that you have already learned chapter 5. Some instructor will start with the later half of chapter 5. So I feel like the beginning of chapter 5 should be covered in this course. So let me try to go through some of the material, and so we're not too much behind in chapter 5 when you are entering your I'll change that later. So let me add the file for 5.1. We talked about a little bit about section 4.1 as we are getting ready for the test. It's normally how we do it in preparation for a test. So 5.1 talking about the term that's called indefinite intervals. Go through a little bit. It felt like more or less like reviewing or your derivative formula. 5.1, the title is called Antiderivative and Indefinite Integration. So starting chapter 5, we're going to talk about integration. Integration is the reverse of differentiation. So in calculus, we are studying the change of a function with two different approach. The derivative calculation is when you have a function, you want to find the derivative. By now, we should already know that derivative allows you to figure out the rate of change of the function. Function model the relation between two quantities, x value and y value. Derivative allows you to find out the change between the relation of the change between the two quantities. So that's why the derivative allows you to find out the speed, allows you to find the acceleration. So derivative is useful. Now, what does integration do is what if you already have the derivative? You want to find what kind of function has this derivative. So it's like if you already know the rate of change, you already know the speed, how far can you go from here to here? So try to know the speed or try to find the distance. That's the reverse. So that's why integration is useful. So fundamentally, if you have a function a capital F and find derivative capital F, you have lowercase f. The lowercase f is a derivative. So and then what if you have the f of x, the lowercase f? You want to find what kind of function had this derivative. So that will be the other direction of differentiation. The inverse of differentiation calculation would be integration process. Now, so we want to be able to identify what can we do with the integration. The integration allows you to solve something called a differential equation. So a differential equation is an equation that has a derivative in there. For example, here we say y prime equal to 2x, or you can also say dy dx equal to 2x. What is y? Right, so this will be the kind of situation that we call differential equation. Any equation that involve differentials or derivatives is called a differential equation. This is a big branch of mathematics, so we can solve all kinds of different differential equations. But in our class, we solve the most fundamental one that you can see in this equation. There's only y prime. A harder differential equation will be y prime plus y double prime equal to 2x. And that will be really difficult to solve because you had two different y value. Now, right now we have y prime equal to 2x. We only have to solve one of the y. So we're solving only one variable y. And that's why compared to the possible differential equation involve more differentials. And this is the initial version of the differential equation. Now, my question will be, if a function had derivative 2x, what is that function? If the derivative equal to 2x, what is y? Any ideas? If the derivative is 2x, what is the original function?
X squared.
X squared, right? X squared. X squared, if the function is equal to x squared, derivative will be 2x. But is that only one? Could be other function that has derivative 2x. What if it's x squared plus 1?
Yeah.
X squared plus 1 derivative also equal to 2x, right? So we're facing the scenario. One way, if you have a function, you find derivative, there's only one derivative. But if you have the derivative, you find the inverse. There may be many, right? There's many functions. The reason for that is derivative tell us a direction, right? But then the curve can have multiple curve, one curve here, one curve here. They all get in the same direction. They're parallel. If they're parallel, they will have the same direction. They will have the same derivative, right? So having the same derivative doesn't mean they're the same function. It only means they're going in the same direction, or they're parallel. So we realize that many functions could have the same derivative. Y equal to x squared, y equal to x squared plus 1, y equal to x squared plus any other number, y equal to x squared plus pi maybe. So basically the equation y prime equal to 2x has many solutions. Therefore, we want to be able to represent those solutions, those like infinite many solutions. How do we represent it? We represent it by a notation. Okay, so we're saying the set of all antiderivatives that have the same derivative is being called indefinite integral. So we call that indefinite integral. So, so then we're saying that we don't have to identify, is it x squared? Is it x squared plus 1? Or is it x squared plus 1, 2, 3, 4, 5, 6, 7, 9? And we give it a common name and say all of these are being called the same thing. So then this is what happens. So we were saying this function y prime equal to 2x. So what is y exactly? Y is equal to the antiderivative, the indefinite integral of 2x. We followed by dx right there. Because if you want to know the change in y, you have to multiply. That's a differential dy, right? If y prime equal to 2x, and then dy equal to the derivative of the y, which is 2x dx. Okay, dy, the dependent variable differential equal to the independent variable times dx. So this echo what we were learning in 4.4. Okay, so essentially this is integration of the dy. Now, what does dy represent? Dy represents small change of the y value. So y is equal to the summation of all those small changes. So in another way, this integration notation are being considered as a continuous version of the summation. You can think of the integration notation as elongated letter s. S is this way, but you drag it, you pull it longer. That's your integration notation. So anyway, this is how we represent all the function that has the same derivative. So basically this notation is saying all the function that has 2x as their derivative, we write it this way. Now we kind of already have a better notation for this. So what kind of function has the 2x as derivative? We know that the function is x squared. But obviously x squared is not unique. So what do? We say x squared plus a number. We don't know what that number is. We'll just put number c. This is a indefinite constant, right? So because we know derivative function that has 2x as derivative, the function must be x squared plus something. We don't know what something that we're adding because we don't know the actual function behavior. So that's kind of also the indefinite part of the integral. Later, we also have definite integral when we know what we're adding, but right now it's called indefinite integral. Basically, indefinite integral is a notation for the collection of all the antiderivatives. All the function that has 2x as derivative is being called an indefinite integral of 2x. If you have to have a formula for it, you will write x squared plus c. Any questions so far? Are we okay? Okay, so let's try to nail this notation a little bit more. So it's more or less kind of like a correspondence between the function and its antiderivative. Okay, so we're gonna write it. I was already writing it there. I was writing x squared plus c. So let's try to explain the notation. If two functions had the same derivative, so f of x have derivative lowercase f of x, capital G of x has derivative f of x. Then what happened to this function? These two functions are very much the same except a number. So in that case, the g of x will equal to the capital Fx plus a number c. So they must be very, very similar. For example, we had an example earlier. The function that has so for example, we had a function that has derivative like f of x is equal to x squared plus 1, all right? And then g of x is equal to x squared plus 9, okay? And obviously the derivative of f of x is equal to 2x, right? And then the derivative of g of x also equal to 2 of x. And you can see these two. And the only differences between them is 9 and 1, and then difference from 9 and 1 is 8. So then for that matter, we see that g of x is equal to f of x except maybe a small difference of the 8. So f of x plus 8, you have 2x. So that kind of illustrate the idea that any function that has the same derivative would have only a number of different input in between them. Any question? Okay, so let's meet tomorrow again. In the meantime, try to finish all of your homework on chapter 4. If you have any question for the solution for the test question, also mention that. We're going to try to centralize our attention on the test practice question. And you have to know that most of the test practice questions are the homework questions. So as we're getting ready from your preparing for the test, you should finish more homework because they are really like one-to-one correspondence, except the number is different. Okay, I'll see you tomorrow. Let me know what question that you have, and we're planning for having the test next Monday. Thank you.
Thank you. I just want to let you know I appreciate all your patience with us.
Thank you, thank you. Well, as long as you guys are following up, and then we can always adjust the schedule based on our pace. See you tomorrow. Thank you. Thank you.